A simultaneous equation model is said to be identified if we can obtain unique estimates of the coefficients in the model. The equations in identified models have a unique structure or statistical form. From this definition, it is clear that equations in a simultaneous equation model must be unique. But what does that mean and why is it necessary? Let us consider a simple example to illustrate the meaning and necessity of identification. Consider the following two equations in a simple demand and supply model. We know that the quantity demanded of a commodity is dependent on its price. Similarly, the quantity supplied of a commodity is also dependent on the price of that commodity. In both equations shown here, quantity is a function of price. But which one is the demand equation and which one is the supply equation? How do we identify and estimate the demand and supply equation? Simply obtaining the data on prices and quantities will not solve this problem. To show why this happens, let us fully specify the demand and supply model with all equations. The demand-supply model shown here has 3 endogenous variables and 3 equations. The third equation is the identity equation showing that the quantity demanded and quantity supplied is the same for every observation. This happens because the quantity sold and the quantity bought by consumers is always the same in a market situation. When data is collected, we can only observe the price that was charged and the quantity that was sold or bought at that price. As a result, the quantity sold and bought is equal in the observed market situation. This means that we can only collect information on the equilibrium point in the diagram, which shows that price and quantity. This point here also shows quantity bought and quantity sold at that price. But to which supply curve or which demand curve does this observation belong? This equilibrium point can belong to any of the supply and demand curves shown here. How do we determine and identify the actual supply or demand curve? Even in the equations, the variables QD and QS will be the same because the quantity bought and quantity sold will be the same for each observation. The independent variable of price is also the same in both equations. Then, we have no way to differentiate the coefficients in these equations because all the variables are similar. How do we determine the coefficients in the demand or supply function? This problem, in essence, is known as the problem of identification in the simultaneous equation models. The demand-supply model we presented in the previous section is clearly not identified. We showed that demand and supply equations have similar variables and structure, that is, they do not have a unique structure or unique statistical form. In this section, we will adjust the equations in this model to make it unique and, therefore, identified. To accomplish this, let us think about a variable that affects only one of the dependent variables in this model. For instance, we know that the income of consumers is an important variable in determining the quantity demanded of a commodity. Suppose we include this income variable in the demand equation of our model. Now this variable of income shifts the demand curve up or down. That is, if income rises, the demand curve will shift upwards. If income falls, the demand curve will shift downwards. On the other hand, the income of consumers will not affect the supply curve. Therefore, the supply curve will stay stable. This situation allows us to identify the supply curve because we will be able to trace the supply function due to the shifts in the demand curve. Let us take a look at the diagram to show how this will work. With changes in income variable, only the demand curve will shift while the supply curve remains stable. At different values of income, we will be able to identify different points where the shifting demand curve will intersect the supply curve. As a result, we can trace out and identify the supply curve. This brings us to an important observation that we were able to identify the supply curve with the help of a variable that was not even a part of the supply equation. That is, we identified the supply equation with the help of the income variable, which was part of the demand equation and was excluded from the supply equation. This is known as the paradox of identification. It means that we can identify an equation by using variables which are excluded from that equation, but included in other equations of the model. Similarly, to identify the demand equation, we can include a variable in the supply equation. The variable should be such that it affects the supply function while the demand function stays stable. So we will be able to identify the demand equation with the help of a variable that is excluded from the demand equation but included in the supply equation. Now that we understand the meaning and importance of identification, let us formally state the conditions of identification. These conditions are known as the order and rank conditions of identification. An equation from a simultaneous equation model is identified only if both these conditions are satisfied. First, let us state the order condition. In the order condition, K is the total number of variables in the model, which includes all the endogenous and exogenous variables. M is the total number of variables in the equation we are considering. For example, it could be the demand equation. Then, M will be all the endogenous and exogenous variables in the demand equation. E is the total number of endogenous variables in the simultaneous equation model. The order condition is satisfied if K minus M is equal to or greater than E minus 1. Order condition is necessary, but not sufficient to determine identification. If this is not satisfied, then the model is unidentified or underidentified. However, if the order condition is satisfied, we move on to test the rank condition. The order condition alone is not enough to establish identification. Now, we move on to the rank condition. The rank condition states that an equation is identified if it has at least one determinant of order E-1 that is non-zero, from the matrix constructed by excluding coefficients from the given equation, but including coefficients from other equations of the model. Hence, we need to construct a matrix of coefficients that contains only the coefficients of variables that are not present in the equation under consideration. Then, we calculate the determinant of that matrix, which will be of the order E-1. If any of the determinants is non-zero, we conclude that the equation is identified. Conversely, if every possible determinant is zero, then the equation is underidentified. While this condition sounds complicated, it is not hard to apply the rank condition in practice if the model does not have too many equations. To illustrate the application of the order and rank condition, let us consider a demand-supply model. In the demand-supply model shown here, the first equation is the demand equation and the second is the supply equation. The third equation is the identity. In the demand equation, we have three independent variables. The price is an endogenous variable, whereas the income and price of a substitute good are exogenous. In the supply equation, price is again an endogenous variable and the cost of raw materials is exogenous. To check whether the equations are identified, we have to apply the order and rank conditions separately to demand and supply equations. Here, we should note two important things. First, we don't need to check the identification of the identity equation because it does not contain any coefficients that have to be estimated. Second, it is possible that one equation of the model is identified while the other is not. So, we must check identification of each equation separately. First, let us check the order condition for both demand and supply equations. We know that K is the total number of variables in the model. Our example model shown here has 6 variables. It has 3 endogenous variables of quantity demanded, quantity supplied, and price. Also, it has 3 exogenous variables of income, price of substitute good, and cost of raw materials. Therefore, K is equal to 6. Similarly, we have 3 equations and 3 endogenous variables in the model, which means that E is equal to 3. M will be different for the demand and supply equation in our example. In the case of demand equation, M is equal to 4 because our demand equation has 4 variables including quantity demanded, price, income, and price of substitute. After solving, we know that the order condition is satisfied for the demand equation as both sides are equal. In the supply equation, m is equal to 3 because the supply equation has three variables including quantity supplied, price, and cost of raw materials. After solving, we know that the order condition is satisfied here as well because k minus m is greater than e minus 1. Therefore, the order condition has been satisfied for the demand as well as the supply equation. Now moving on to the rank condition, we have to set up the equations and their coefficients in a specific format. First, let us bring all the variables of our model to the same side of the equation. The variables quantity demanded and quantity supplied have changed signs here because we brought them to the right-hand side. Second, we can construct a table using the equations shown here. The table shows the values of the coefficients attached to each variable in all the equations of the model. For instance, the first row here shows all the coefficients of the demand equation. The coefficient associated with price in demand equation is beta 2, so we have mentioned beta 2. Similarly, the demand equation does not contain the variable r, which shows the cost of raw materials. Therefore, we have mentioned 0 here. This way, we have represented all the coefficients and their values in every equation of the model. Finally, we construct a matrix from these coefficients as they appear in the table. The first row of the matrix here shows the coefficients of the demand equation. The last two elements are 0 because the quantity supplied and cost of raw material are not present in the demand equation as we observed in the table. The second row represents the coefficients of the supply equation. The first, third, and fourth elements here are 0 because quantity demanded, income, and price of substitute are absent from the supply equation. The third row represents the identity equation coefficients, which are simply -1 and 1 because it contains only the quantity demanded and supplied. Now, we are ready to check the rank condition using this matrix. First, let us check the rank condition for the demand equation. If we read the rank condition carefully, we notice that we have to consider only the coefficients and variables that do not appear in the demand equation. As a result, we have to remove all the coefficients and variables that appear in the demand equation. Therefore, we cancel out the entire first row of the matrix because it represents the demand equation coefficients. Next, we cancel out the first four columns of this matrix because they represent coefficients of price, income, price of substitute, and quantity demanded. All of these appeared in the demand equation. After all this, we are left with a 2 by 2 matrix. This matrix shows the coefficients that are excluded from the demand equation. Hence, we calculate the determinant of order e-1 from this matrix. Only one such determinant is possible, which is equal to -alpha3. Since this determinant is non-zero, we can conclude that the demand equation is identified. For the supply equation, we can follow a similar procedure as well. We have to remove all the coefficients and variables that appear in the supply equation. So, we remove the entire middle row of supply equation. Then we remove the second, fifth, and sixth columns because they belong to price, quantity supplied, and cost of raw materials which appear in the supply equation. We are left with a 2 by 3 matrix. From this matrix, we can construct three determinants of order e-1. But, we only need one of the determinants to be non-zero for identification. We can see here that the first determinant is equal to beta 3. Similarly, the second determinant is 0 and the third is equal to beta 4. Since we need at least one non-zero determinant, we can conclude that the supply equation is identified. To determine whether an equation is exactly identified or over-identified, we have to revisit the order condition. In the previous section, we determined that the demand and supply equations are identified. Now, let us see if they are exactly identified or over-identified. In the case of demand equation, the order condition states that k minus m is equal to e-1. This means that the demand equation is exactly or just identified because both sides are equal. This implies that we have exactly the number of exogenous and excluded variables to estimate the coefficients of the demand equation. Exactly or just identified models can also be estimated using indirect least squares. In the supply equation, K minus M is greater than E minus 1. This implies that the supply equation is over-identified and we have more information in the model than needed to estimate the supply equation. The method of indirect least squares cannot be applied to models that are over-identified. Over-identification is not a bad property to have, it simply needs a different method of estimation such as 2SLS. If the order or rank conditions are not satisfied, it means that the equations are unidentified or under-identified. These equations cannot be estimated using any method until they are made exactly or over-identified. Thank you for watching, and I will see you in the next tutorial.